System and environment. The fundamental concept of energy was explained by Richard Feynman, a Nobel Prize-winning physicist. There is a fact, or if you wish, a law governing all natural phenomena that is known to date. There is no known exception to this law. It is exact so far as we know. This law is called the conservation of energy. It states that there is a certain quantity, which we call energy, that does not change in the manifold changes which nature undergoes. And this is from the Feynman Lectures on Physics, mainly Mechanics, Radiation and Heat, copyright 1963. The concept of energy is so fundamental, like space and time, that there is no real good definition of what it is. However, just like space and time, that doesn't stop us from doing very useful calculations with energy. Energy is related to motion and forces. It can be stored. It can be changed from one form to another, such as light to thermal energy, mechanical to thermal energy, gravitational potential energy to kinetic energy, and of course many others. It can be measured and compared, and it cannot be created or destroyed. In order to perform calculations with energy, physical boundaries need to be set. The physical boundaries are based on the system and the environment. A system is a small segment of the universe that will be considered in solving a specific problem, and we will erect a boundary around it. The environment is everything else outside the system boundary. The system can be a particle, a group of particles, an object, an area of space, and its size and shape is totally determined by how you want to solve the problem. So why are we defining a system and its environment? So we can make the problem solvable. By defining an appropriate system, we can isolate the forces and the matter that are within the system from the forces that act on the environment and the matter outside the environment. If the only forces are internal to the system and no matter crosses the boundary between system and environment, then there is no change in the energy of the system. External forces and matter moving across the boundary will change the energy of the system. Let's give some examples. The moon, up here, exerts a gravitational force on the Earth, so it must exert a force on every object on the Earth. Why then, when we work out the motion of a drop ball near the surface of the Earth, don't we need to take into account the effect of the moon's gravity? Or for that matter, the gravitational force from the sun and all the other planets, and, three dots there mean, etc., etc. When we solve for the motion of a dropped ball, we only consider the gravitational pull of the Earth because the Earth's gravitational force on the ball is so much greater than the gravitational force of the moon and everything else on the ball that we can ignore everything but the ball and the Earth when solving the problem. So even though every object in the universe affects every other object in the universe, most of the effects on any one object are too tiny to care about. Often we can just consider one object or a small number of objects and ignore everything else. To solve problems, we divide the universe between what we want to study, that's over here, and this dashed line here is the boundary, and everything else. How's that for a technical word? And the whole box there is representing the universe. A system may consist of one or more objects or amount of material in a region of space. We put an imaginary boundary or picture frame around the system. Everything outside the system is defined as the environment. Forces that are internal to the system, that is, they do not act on the environment, do not change the total mechanical energy of the system. For example, if this object, you have two objects here, and they bounce off each other, they each exert a force on each other, and that will not change the total mechanical energy of the system. There are three different types of systems depending on whether mass, energy, and/or forces can move or be transferred between the environment and the system: open, closed, and isolated. Open systems can both act on and be acted upon by the environment. Objects might be able to leave. For example, this object here is about to leave the open system, and this object here is about to come in. Some outside external forces from the environment can affect the objects in the system. Forces inside the system can affect the environment. energy can be transferred into and out of the system. Our energy symbol is right here. So here you have energy or forces acting through the barrier on the open system. And here is energy leaving the system, or forces acting through the barrier. A closed system does not allow the movement of mass through the system-environment boundary. Objects cannot move into the system or move out of the system. So let's look at our objects again. These objects are not going through the barrier, and external objects or masses are staying outside the closed system. External forces can still affect the objects in the system. Forces inside the system can affect the environment, and energy can be transferred into and out of the system. Here's our energy going through the barrier into the system and forces, and here's our energy or forces leaving the system through the boundary. An isolated system is a special case of a closed system. Neither energy or mass can transfer across the system boundary. Objects cannot move into the system or move out of the system. External forces cannot affect the objects in the system. Forces inside the system cannot affect the environment. Energy cannot be transferred into and out of the system.